So on this page of today's notes, what you're seeing is that rectangles are being represented, as we know, as having all the properties of a parallelogram. So everything we learned last class about parallelograms are true for rectangles. In addition to that, we've got a definition of a rectangle. As Canyon suggested, it's a quadrilateral with 4 right, or you could say congruent angles. But there's something else that's true about a rectangle that wasn't true of our parallelograms. What else do you think is true? Let's talk about the parallelogram attributes first of all. In addition to the definition, which says all sides are parallel, are we good with that? These sides are all parallel, or opposite sides are parallel. Remember, we also said that 2 pairs of opposite sides are congruent. Is that still true? What are some of the other properties of parallelograms? Good. Consecutive interior angles are supplementary, add up to 180. Now that they're 90 degrees, don't they still add up to 180? Sure. What are some other attributes that were true of parallelograms? Okay, true. Exterior angles add up to 360. What about the diagonals? Good point. And we use that to prove all kinds of things. What about the diagonals themselves, their lengths? Are they congruent here? Let me give you an extreme example. If I draw myself a really exaggerated parallelogram, can we agree that diagonal 1 and diagonal 2 are not the same size? Seems easy to see that. What about in a parallelogram? I mean, a rectangle. They are the same? How do we know? Okay, hold on. Let me listen to the thing for a second. The sides are all equal. Opposite sides are equal. So why does that make the diagonals the same? If they're all equal, but isn't that true also here in the parallelogram? Okay, so why is that different? Like, we got to be able to convey to people why the 90-degree add-on makes it so the diagonals are now congruent. Marco?
If the sides are the same, just separate the two, right? It would, due to the Pythagorean Theorem, you would have the.
Oh, interesting. So your suggestion is that since this is a right angle and this is a right angle, we know that this side is the same as this side. They share this side because it's reflexive. And that means that if I knew this length and I knew this length, I could find this using the Pythagorean theorem. And then I could find this using the Pythagorean theorem. And since I'm using the same A and the same B, my C would be the same as well. Clever. Yes, buy that? Okay. Another way to think about it, of course, is what we've done, which is prove the 2 triangles are congruent. Same idea, this side and this side are congruent. This is reflexive. Because these angles are both right, we could say that they're congruent. So by side, angle, side, side, angle, side, these 2 triangles are congruent. That means by CP, CTC, the diagonals are congruent. So yes, that is the number 2 here, the additional reason, the additional fact about rectangles. Diagonals are congruent. Someone was asking me before class if I find geometry gets boring after teaching it so many times. And I wanted to share one little story about how it came into play with this diagonals being congruent. I was doing some work on my house and I was replacing some windows. And the contractor came in and he said, okay, I'm going to put in a 3-foot board here and a 3-foot board here and a 2-foot board here and a 2-foot board here. And that way I know it's a rectangle. Is that a rectangle? Does it have to be a rectangle? It's a quadrilateral for sure. Could it be a parallelogram? Because we can't see the right angles, and that's the distinguishing factor. And so this contractor says, no. If opposite sides are congruent, it's a rectangle. And I said, that's not true. I could have those same length of sides, 2, 3, 3, and 2, and it can be all kinds of skewed up. So what I said to the contractor is, I know how to confirm that this is in fact a rectangle and not a parallelogram with the same dimensions. What did I tell him to do? To measure the angles. It's really hard to measure angles. Like, is it 90 degrees or 89 degrees or 89.6? It's really hard to measure angles like that.
Check the diagonals.
Right? We can measure from this corner to this corner. And if that measurement ends up being the same as from this corner to this corner, then in fact, it is a rectangle. When he puts the window in, it's not going to shatter from the pressures. And that's what worked. Real life applications of parallelograms. Okay. For today, 1/3 of your activity will be spent working with rectangles. Again, it's going to use all these same attributes we used last class with parallelograms, plus these 2 new ones. Let's do this first one together. Actually, let's do number 2 together. So it tells us we're looking for AC. AC appears to be a diagonal. What should I use to determine the length of AC? Good. Because we know that even though this is a rectangle, it's also a parallelogram. And in a parallelogram, the diagonals bisect each other. So if this part is 15, how much is EC?
15.
Also 15, which means AC is the sum, or 30. All right, BD. Oh, well, that's totally on the other side. How am I going to know that? Good, because it's a rectangle, which it says up here, I know that the diagonals are the same length. So if AC was 30, so is BD. All right, BE, 15, because it's half of the 30, it's bisected. What about AB? Good, because opposite sides in a parallelogram, and thus in a rectangle, are congruent. This seems easy. What about BC? Very good. Pythagorean theorem can apply and be used only in what circumstances? If it's got a right angle. Fortunately, this is a rectangle. It's got a right angle. So I can think of it as a right triangle, where this is my unknown. I've got 27 up here and 30 here. So I can do Pythagorean theorem, which is supposed to be a squared plus b squared equals c squared. How do I know which piece goes where? Good. If these two add up to be this bigger one, doesn't this one have to be the biggest? And the biggest is always the side opposite the biggest angle. We learned that in a triangle, there can be at most one right angle, and there cannot be an obtuse angle in that same triangle. So this is the biggest. So we should have x squared plus 27 squared equals 30 squared. So x squared plus, what is it? 27 is 9 times 3, so it's 81 times 729 maybe? 729 equals 900. Subtract 729, x squared is equal to 271. 171.
It's one.
171, which means x is equal to square root of 171. And although we could probably divide some things out of that, like 9 comes out of that, I'm okay with just leaving it as the square root of 171 for now. Any questions on problem number 2 here as a model of how we're going to solve these problems? 5, this seems easy. I got this. 3, I'm going to be looking at the notes to see what the rules are because I haven't memorized those yet, but I can apply these. 1, I don't believe in rectangles. Okay, good. Hands down, please. You'll notice that 4 and 3, for that matter, are different. What makes these different problems? Yeah, what makes 3 and 4 different from 1 and 2, though? They're all about angles. So let's do number 4. X, W, Y. X, W, Y. So I'm looking at this angle. How can I possibly know what that angle measure is? Ah, but we can find it, can't we?
Yes.
Yeah,
Wait, because
I'm waiting.
if it's a rectangle and it's like the 90-degree angle, would it be 45?
Good question. We don't know that a rectangle's diagonals bisect the right angles. In fact, they don't unless it's a square. That'd make it too easy. But we do know that the diagonals are what in a rectangle? Congruent. And because it's a parallelogram, they also do what to each other? Bisect. So WY and XC are the same length, aren't they? And that means that WV and XV are also the same length. They're each half of the same thing. So if I put those marks there, what kind of triangle is this? Isosceles, which means the two base angles are the same. So if I've used up 64 degrees in this triangle, 180 minus 64 leaves 116, and it's going to be split evenly among these two. Each of them is 58 degrees. So X, W, Y is 58 degrees. What about this next piece? Y, X, Z. How could I find this one? Good, we could. Yeah, so Kenyon said we could do that linear pair here, say this is 116 and do the same idea there. Or Lillian, what'd you say?
90 minus 58.
Yeah, because we know that this angle X is 90 degrees. So we could say 90 minus 58, which is equal to 32. So this angle is 32. WVZ, WVZ. This is what you suggested with the linear pair, right? So that's 116. XWZ, well, that's a right angle. And XZY. What about that one? Okay, you could do that again, or you could recognize that because it's a parallelogram, it's an alternate interior angle with this 58 up here, isn't it?
That's back.
All right, so I'm going to leave you to the rest of this particular page. Let's move on to the next page, which is the rhombus, or the plural of which is rhombi. And what's going to change here? What's the definition of a rhombus?
Quadrilateral,
Yes,
parallelogram.
it is a parallelogram. We're not going to put that in the definition. I'll explain why in just a minute. We want the definition to be simple. The smallest piece of information necessary to make it definitely a rhombus. Yes. So a square is not a rhombus? Remember last class, we did the Euler diagram? We did p-grams. We did rectangle. We did rhombus, and this little area in the middle is square, shared by both of them. So a square is a rectangle and a rhombus, which means no, we can't just say that one's obtuse and one's not. What about side lengths? All equal. That's the definition. So let's put that into our definition thing here. First one here. Definition, it's a quadrilateral. With 4 congruent sides. And we could, if we wanted to, make it a more complicated definition. It's a parallelogram that has 4 congruent sides and diagonals are bisected and blah, blah, blah. We could make all sorts of rules, but that means if you were going to try to prove that something is a rhombus, you'd have to prove all those elements. It's easier to find just the pure essential difference. So in addition to regular parallelogram things, let's see what changes in a rhombus. I'm going to draw in this diagonal, and what do you notice I produce? Isosceles triangles, which is new for us. What do we know about the isosceles triangle theorem says about base angles? So these two are the same. And these two are the same. But wait a minute, don't we know that this one and this one are the same because they're alternate interior angles? Yes. So that's our next one here is diagonals bisect the interior angles. And this is the first time that happened. It didn't happen in the rectangle. I think Braden was hoping it was going to in the rectangle to make that nice and easy for the 45s, right? But this is the first time it comes up. Okay, so one more piece that we're going to bring in for rhombus. If I draw this other diagonal, what happens? Different two isosceles. So these two will be the same and these two will be the same, right? What do you notice about all 4 of these triangles? Are they right triangles? They're all congruent, aren't they? Angle, side, angle, angle, side, angle, angle, side, angle, angle, side, angle. If they are all congruent, then these little angles here in the middle must also be congruent. And if this is a full spin around 360, it's got to be divided evenly by 4, which makes them each 90, which makes Kenyon's assertion that they're all right angles accurate. That's the last piece here, which is diagonals are perpendicular. So because we're seeing perpendicular diagonals, we're going to know there's a right angle here, which means we know we're going to get some more Pythagorean theorem stuff. EF is 23. The fact that DF is 40, it'd be hard for me to mark this as 40 and know I'm talking about the whole length. So how can I mark this better? 20 on each side, because we know because it's a parallelogram, it's bisected. One of our questions here is going to ask us for GH. How can I find that? Good. Because if this side is 23 and it's a rhombus, then all the sides are 23. All these triangles are going to be congruent. And in this triangle, what we've got is, wait, which one's going to go by itself? Is it x squared plus 20 squared equals 23 squared, or 23 squared plus 20 squared equals x squared, or what? Yes. X squared plus 20 squared equals 23 squared. X squared plus 400 equals 529. X squared is 129, so X is the square root of 129. And then when it asks for GE, what's that going to be? Yeah, just double 2 root 129. We've already done HF as 20, GF is 23. Easy peasy. Okay, the last shape for today is a square. And the square is that illegitimate love child of a rhombus and a rectangle. And it gets all their attributes, but nothing new by itself. So you have the rest of this period, which is 2:36. So just over an hour to work on this packet. I also want to make this time available to those that wish to take the Unit 5 test for another try. You'll come up to me and let me put in your name. If you haven't taken the Algebra Skills Survey, we also should get that done. That's a 45-minute test. Okay, you've got the hour to do what you need to do.